7, 8, 9, 10, 10, 10, 10, 10.
It'll almost be too easy.
That's too easy! Why did you say that?
Counting to 10.
It's not possible.
No.
Hey!
I gotta get out of here! I gotta get out of here! I'm down! Get a hold of yourself!
Live from Wade Studios at Mr. Wade's house, we've got section 10-1, but guess what? This is the 150th episode of The Evolution of Wade.
Series will air its 150th episode this Friday.
Celebrates its 150th episode tonight.
150 episodes.
So we go back to limits now in this chapter 10, and we start looking at limits that you can't do based on what I taught you in chapter 8. So we need some new techniques here, and some of them are very interesting, creative, unusual techniques. So if I had given you this limit on the chapter 8 test, you could not have done it. What's the first thing we do with limits? Take that 2, plug it in for both of the x's, and just see what happens, right? That's where we always start a limit anyway. Well, 2 to the 4th is 16. 16 minus 16 is 0. Plug in 2. On the bottom, 2 to the 5th is 32 minus 32 is 0. What a shocker. Most limits in calculus are 0 over 0, or sometimes infinity over infinity. Matter of fact, didn't we have some indeterminate conversations back in chapter 8? We're going to have more in this chapter right here. In chapter 8, we said 0 over 0, infinity over infinity, and infinity minus infinity were 3 indeterminate forms that literally could equal 7, 54, 22.5. You never know what these are going to turn out to equal, okay? That tells you nothing. Only in BC, but not in AB, we're going to discuss indeterminate forms 4, 5, 6, and 7 in this chapter. There are 4 more to go, and one is going to blow your mind. You won't even believe me at first, all right? So let's go back to this. 0 over 0, that's a bad place to be. Okay, so what were our techniques in chapter 8? Well, algebra. Remember, we could factor, right? So you could try to factor the top. Actually, the top is the difference of 2 squares, I should note. The top would factor into x squared minus 4 times x squared plus 4, anyone? See that? But then the bottom is the difference of 2 quintics, x to the 5th and 2 to the 5th. Okay, remember me mentioning like quartics, quintics before? 32 is a perfect quintic because it's 2 to the 5th. I think I mentioned before that there's a website that actually tells you how to factor fifths and sevenths and ninths and all the odd powers. The even powers are just difference of 2 squares, always. The odd powers, lots of luck. Nobody's going to memorize that formula that's like as long as this entire room right here. There's no point. You're not going to be able to factor x to the 5th minus 32 on the fly. Total dead end. There was something else we did, though. You remember the limit as x approaches c? And it was f of x minus f of c over x minus c. We called this the limit definition of the derivative at a point. Doesn't all this just mean take the derivative, plug in c, find f prime of c? Remember this tactic right here? Okay. This does not fit that form at all. Not one bit. C and c have to match. That's 2, that's 32. Okay, so this is worthless for this problem. Factoring is worthless for this problem, and it's indeterminate. What in the world do? There is something very clever. It turns out, and this is going to be strange, okay? But it turns out that if you take the derivative of the top and the bottom separately, this works. As long as you're in the indeterminate form, this works, okay? We just established indeterminate form. That's why you plug in the 2. You can take the limit as x approaches 2. You can take the derivative of the top separately. 16 goes to 0, but x to the 4th goes to 4x cubed. The derivative of the denominator would be 5x to the 4th minus 0, which is 5x to the 4th. Okay? You can retry the 2 now, and if it works, that's the limit. Now, now wait a minute. If you took the derivative of a fraction in the first semester, you had to do the whole quotient rule, ho d hi minus hi d ho over ho squared, and we didn't even do that right there. This is the only time in all of calculus ever that you will take a separate derivative of the numerator and a separate derivative of the denominator and get away with it. But if you're in the indeterminate form, this works. Would you plug in 2 now? You could. I wouldn't. I'd rather reduce it first and make it a little bit better, right? Let's not do 2 to the 3rd, 2 to the 4th if we don't have to. So I'd rather take out an x cubed. Let's actually rewrite this. So this is just algebra. This is not calculus anymore. The first step was calculus. This would be 4 over 5x if you reduce it. Now plug in 2, and it will not be indeterminate. There's not even a 0 on the bottom anymore, so I know it's not going to be indeterminate. There's not a 0 on the top. Plug in 2. You get 4 over 10, which is 2/5. Weird, but true. All right? So, answer is 2/5. Now, we mentioned this in chapter 8. There is only one time where a function does not exist, but its limit does exist, in a finite sense, that is. Did the equation exist at 2? No, because as soon as we plugged in 2 to the bottom, we noticed there was a 0 on the bottom, right? There was also a 0 on the top, which made it extra weird, but whatever the graph of this crazy function looks like, it can't exist at 2 because there's a 0 on the bottom, okay? And if it doesn't exist, wouldn't that be a hole, a vertical asymptote, or a jump? Now, this is not a piecewise function, so there's no jump, okay? It's either a vertical asymptote or a hole. We ended up getting a limit. See, when you approach a vertical asymptote, which we really haven't quite done yet, but when you approach a vertical asymptote, it's going to force you upward or it's going to force you downward to infinity or negative infinity. If you get a finite outcome, that means that even though this function does not exist at 2, it has a limit from both sides, not right side, not left side, from both sides. There is a limit that is in agreement. So I kind of want you to understand what this means. Who cares what this graph looks like, but guess what? Somewhere on the graph, you have the point 2, comma, 2/5. But it's a whole, because only a whole could have a limit in agreement from both sides, and they do agree from both sides at 2/5, because that's what the math told us, but it does not exist there. Okay, so you had just proven the existence of a whole. So now let's look at letter B, which would have been unsolvable by our means in chapter 8. But now we've got the tools to do it because we just earned a new superhero power today, didn't we? The power to take the derivative of the top and the bottom and retry. Weird. So take 0, plug it in first. Let's test out the 0. Cosine of 0, if you remember on the cosine graph, is a peak. It's 1. 1 minus 1 is 0. Suspicious. And 0 squared minus 0 is also 0. Okay, so this is the indeterminate form 0 over 0. Now remember that rule I just showed you? Okay, it's got a name. We're getting to that, of course. It's got a history, a very sordid history. We're getting to that as well. So the only time you can use this new rule I'm showing you is not just any of the 7 indeterminate forms. It only works for 0 over 0 and infinity over infinity. So it's the first 2 indeterminate forms we ever did in chapter 8. Okay? So to use this rule, you must get to 0 over 0 or infinity over infinity. We do have 0 over 0. There is no method in chapter 8 that would solve this. However, we can take the derivative of the top and the derivative of the bottom separately and retry. And if that doesn't work, you may have to take the derivative again. Okay, we might have a double case or a triple case. Eventually you get to a point where you're going to have a determinate form. Until later in the chapter where there are some where you could go through an infinite loop and never escape the indeterminate form. Those have different tactics. That's only for BC class. Wait till we get to those. All right, let's take the derivative. Isn't the derivative of cosine negative sine? So I'm going to put negative. I'll leave a little strategic gap right there. Negative sine of 2x, chain rule 2. Let's promote that to a coefficient. Negative 2 sine of 2x. 1 becomes 0. And that's going to be 2x minus 1. Okay? Take a derivative, retry. Take 0, plug it in. The sine of 0 is 0 times negative 2 is 0 on top. Oh no, we're going to get indeterminate form again. Nope. Take 0, plug it in the bottom. 0 minus 1 is negative 1. Determinate. It is okay to have 0 over a non-zero, right? 0 over anything is 0. That is a determinate answer. And if you circle a 0 in Mr. Wade's class, it makes a donut. Put some sprinkles on there. Donuts. Okay, so it turns out, whatever this graph looks like, not that you have to know that, it does not exist at x equals 0 because it failed on the denominator. But the limit from both sides agrees and approaches 0. That's 0, 0. That's the origin. There's a hole at the origin. So you just prove the existence of a hole. Okay? Interesting. All right. Let's go to the next category. This thing has a name. And the name of that thing we'll put in this little box right here. L apostrophe. Now, those of you who have French class will recognize the punctuation. If you've never had French, you won't recognize this. I had 3 years of French in high school. L apostrophe H O. You put the little caret over it. P-I-T-A-L apostrophe S, rule. Okay, if you think that looks like hospital, that's actually French for the word hospital. But it is called l'hôpital. The H is silent in French. So this is called L'Hôpital's rule. Who is it named after? A guy whose last name was L'Hôpital. And that's going to go in the other blank. It was 1696. His first name was Guillaume. I've asked this question for 30 years as a calculus teacher. Nobody's ever given me the correct answer for some reason. I always ask people, Guillaume is French for what very popular common English name? First name of a male. Well, you can kind of see the I-L-L-A-M in there. Let's just pull out the I-L-L-A and the M. Can you kind of see that it's William? There is a Spanish name, Guillermo. Guillermo is really close to this. That's Spanish basically for William. Okay? So this is actually William is who this is. And his surname, or his last name, we're going to run out of room here, but maybe you won't. De, lowercase l. It's capital over here because it's a rule. But in French, it's actually lowercase for people's last names. And then capital H-O-U. P-I-T-A-L. So his name was Guillaume de l'Hôpital, or maybe in English we could just call him Bill Hospital, right? Okay, so that is L'Hôpital's rule is what we'll call it. This is leading to a big controversy though. We're getting to that in a history break. But now in the blank. Okay, so when does this work, right? It works in the blank form. Didn't we say it had to be in the indeterminate form, right? So we could put in, let's just abbreviate this, indeter, but wait a minute. Not just any indeterminate form. Doesn't it have to be 0 over 0 or infinity over infinity? So you may want to put all that in the blank right there. As long as you're in the indeterminate form. You can retry the limit. Now look at your paper, what it says there, okay? It says retry the limit with f prime of x over g prime of x. If that doesn't work, retry the limit with f double prime over g double prime and just keep taking the derivative of top and bottom. As soon as you depart the indeterminate form, you should be able to get your answer at that moment, right there, okay? Really interesting stuff. All right, let's see if we can apply it to yet another one. By the way, this guy here, he was extremely wealthy. Most of the mathematicians were probably middle class. A few were like dirt poor, but most of them were probably middle class and had the means to get an education, learn mathematics. Most of those, top 100 guys. This guy's not in the top 100, by the way. He's not ranked at all. We're about to find out why. But he was extremely rich, and it was actually part of the French nobility. So this guy he was a big shot, all right? That's kind of what got him into the hot water of this whole story that we're about to come to anyway. All right, let's try letter C. So it's the limit as x approaches 0 of this fraction. Now, chapter 8, lots of luck. Can't do much with it, okay? The more advanced limits are in this chapter. So you could plug in 0 first. You would get 0 on top, clearly, okay? On the bottom, you would get e to the 0 is 1 minus 0 minus 1. Oh, so clever, Mr. Wade. You set that up as 1 minus 1, didn't you? Yep, I did. It's 0 over 0, okay? You see these in college all the time, too. So, all right, indeterminate form, but luckily it's in the L'Hôpital form, so we can use L'Hôpital's rule. It is one of those two indeterminate forms that are allowed. So the limit as x approaches 0 of, okay, let's retry the derivative of the numerator, what we call f prime of x. That would be 16x to the first. The derivative of e to the x, do you remember this one? It is itself, because it's growth or decay. It's itself times the natural log of the base, so natural log of e, which is just 1 anyway, times the chain rule of x, which is also times 1. It's one of those rare derivatives that is itself. Minus 1 from the x, and then minus 0 from the 1. Okay, there is my new limit. Let's plug in 0, and we get 16 times 0 on the top. Well, that doesn't help. Okay, but that's okay. If the bottom works, we're good. E to the 0 is 1 minus 1 is 0. Mr. Wade, you clever cat. All right, I gave you one that was 0 over 0 twice in a row. Okay, you can even make your own, by the way, at home. So now, since it's still indeterminate, since it's still 0 over 0, we can take another derivative and try it again. Derivative of 16x is 16. I believe we have now departed the indeterminate world because guess what? It's not going to be 0 over 0 this time. It's going to be 16 over something. So we can now solve the problem. Let's find out what happens. E to the x derivative, isn't that just itself? Again, isn't minus 1 just 0? Plug in 0, and you get 16 over e to the 0, which is 1. So 16 over 1 is 16, final answer. And let's realize that we just showed two things. Number one, we showed that 0 over 0 can approach 16, right? That's why 0 over 0 is indeterminate, because you don't know what it's going to turn out to be. Number two, the limit from both sides of 0 created a 16. That means the limit agrees. But the function did not exist. This original function here, this graph did not exist at 0 because you got a 0 on the bottom. Therefore, there must be a hole at 0, 16. There you go. All right, let's try letter D. Hey, look at this. It's a piecewise function. We haven't done one of those in a while. All right, so we've got this really wacky curve, which I kind of graphed for you. It's this weird little thing that kind of goes into a little hole right here. And so this equation is going to be defined in the piecewise function. Now, back in the old days, back in the first semester, we used to say like x greater than or equal to 1, and then the other one was x less than 1, right? Or x less than or equal to 7, x greater than 7. We would kind of do like the greater and less than type thing. This is also a type of piecewise function we've never talked about. This is going to be the graph everywhere in the world except for 0. See how it says x is not equal to 0? So basically everywhere but right on the y-axis where x equals 0, it's going to be this curve that I've drawn. At that one instant, at x equals 0, we're going to let the value be 2k, whatever that is. I just graphed it up here. It's just a little closed dot at 2k. We don't even know what k is. K could be negative. The dot could be down here. I just put it up here as positive. So you've got a curve and then a dot. Okay. Now, first of all, I wonder why I avoided the 0 in the first place. Oh, if you plug in 0, you'll get a 0 on the bottom, so this function doesn't even exist at 0. I've kind of shown you that it has a hole. So that's kind of why we're dodging 0. And then we have this floating point somewhere, but the point's kind of flexible because we don't know what k is. So let's start with this. Okay, the very first question you see on your paper there, it says find the coordinates of the hole. We've just been talking about this. The coordinates of the hole are the limit from both sides as x approaches what? As x approaches 0, you're going to focus in and try to find out what the y is focusing in on. That's what a limit is from chapter 8, right? So we're going to take the limit as x gets super close to 0. Since you can't really get there, there's a hole in the ground. But the cars can drive like right up to it where their bumpers are like hanging out over the hole. And they can get as close as they can, right? What happens when you go towards 0 for this crazy curve? All right, x plus 1 minus cosine of x over x. Didn't we just say that when we do L'Hopital's rule, like you're at, or not just L'Hopital's rule, any limit back in chapter 8, if it was a finite limit, aren't you finding the coordinate of a hole? Of course. Take 0, plug it in. I believe you'll find that there's a 0 on the bottom, which means discontinuity, which means hole, vertical asymptote, or jump. Okay? Jumps are only for piecewise functions, and I know this is a piecewise function, but I'm only focusing on just this one single function by itself right now. So just this one single function couldn't be its own piecewise, not that. So this thing either has a vertical asymptote or a hole. Well, I told you there was a hole, so we know it is. Okay? If you plug 0 into the top, you also get 0. What a shocker, you get 0 over 0. Okay? Most of the limits are 0 over 0, at least in AB calculus, and then a lot of them in BC. So, all right, that's indeterminate, but it's in a L'Hopital form, so that's good news. So let me try L'Hopital's rule, because you can't do anything else but L'Hopital's rule with this one right here. There's nothing else to do in math that'll work. So let's do this. The limit as x approaches 0 of the derivative of x is 1, the derivative of 1 is 0, the derivative of minus cosine of x is a positive sine of x, with a chain rule from the x of a times 1, by the way. And the derivative of x on the bottom is 1. Well, we didn't get 0 over 0 because of that 1 downstairs. We've escaped the indeterminate form. Take 0, plug it in, and you get 1 plus sine of 0. Sine goes through the origin, right? Here's the origin right here. Sine of 0 is 0. 1 plus 0 over 1 is 1. Okay. So now if I just said find the limit, you would stop right there and tell me 1 was the final answer. 1 is the limit. But if it says find the coordinates of the hole for the first time today, we're going to say, well, it approached 0 from both sides. And apparently the y coordinates, which is what a limit is, are zeroing in on 1. So that coordinate is 0, 1. You can see it right there. Okay? So 0, 1 is your official answer. All right? Now let's go to the next thing it says. Because the limit exists, this proves that, and of course the limit did exist, it was 1, right? This proves that there is a, okay, we basically said this already, hole in the graph because the limit exists, right? At x equals 0. That's the first blank. Now the second blank says find the value of k that makes f continuous. But Mr. Wade, f is not continuous, it's discontinuous. There's a hole, and it's not just a hole, it's a holy jump, right? There's a jump and a hole. Wait a minute. Didn't we say that k was unknown, but k could kind of be controlled by us? We just need to find the only k value in the world that would slide this point down here and cover up the hole and make it completely continuous. We're going to patch the hole. So I want to move that blue dot down to there. Then we would make a continuous function. Now that's kind of clever. That's a way that they could ask it on the AP test and in college. So find the value of k that would make this continuous. Well, guess what? If 2k is the y-coordinate up there, but I really want, what was the y-coordinate? 1? Isn't that really 0, 1? If I want 2k to equal 1, divide both sides by 2, the answer is k equals 1/2. That's all you have to do. Just plug in the number that makes that scoot down and close up the hole. Now you have a continuous function. Problem solved. All right, so now let's play Match That Math Guy. Okay, so 4 choices on the board, please. Who discovered L'Hopital's rule? Just talked about that, right? I bet we can guess. The logarithmic loop, remember integrated 3? Log base 2 of x equals 5, so you do 2 to the 5th equals x. You remember this, the loop we used to do? Okay. Partial fractions, chapter 4, genius, right? The mathematician who handed Euler his official PhD in math. Good friend of the family, by the way. And this is also the guy who defended Leibniz in the big rivalry between Leibniz and Newton when Newton falsely accused Leibniz of stealing calculus. Who is this famous mathematician? Well, he discovered L'Hopital's rule, so it's got to be L'Hopital, right? Nope. L'Hopital stole it. The person who discovered L'Hopital's rule was letter B, number 81, Johann Bernoulli. Johann was the one responsible for all this stuff. We didn't mention any L'Hopital with partial fractions in the first semester, not with the logarithmic loop back in integrated 3. That son of a gun. We're getting to the story, all right? Now, let's look at the second line. Maybe he discovered this. Bernoulli's principle. Must have been one of the Bernoulli boys, right? Bernoulli's principle, and by the way, that allows our modern cars to actually work, and this was discovered way before we even thought of cars, but we needed this. Also, aerodynamics. Long before we had airplanes. This person, with his good buddy number 1 Euler, figured out all the aerodynamics that would lead to the Wright brothers and the modern jets. That would be number 101 ranked, Daniel Bernoulli. Letter C. The son of Johann Bernoulli. What a smart family. I told you before, I've told you in integrated 3 and calculus both, that the Bernoullis were like the royal family of mathematics. I mean, as far as talent goes, they weren't necessarily that rich. But third mathematician discovered the number E, as mentioned back in the PERT formula in integrated 3. Remember A equals PE to the RT? Discovered separation of variables. That was the first semester. Remember these little guys down here? Where you had to like divide both sides by y, get the y underneath and get the dx back up. I'm not even filming it right now. Remember this? Where the y divides down, the dx divides up. Differential equations, right? Separation of variables. Also came up with the integral symbol. Oh, you know who this is, right? This is number 53 ranked, Jacob Bernoulli. Letter A. And Jacob, of course, was the older brother of Johann Bernoulli and the uncle to Daniel Bernoulli. So major discoveries in this one family. And there are more Bernoullis too. There are about 14 of them that were all mathematicians. The last one discovered the length, remember arc length from the last chapter? Discovered the arc length, but only on the natural log curve. And only after another mathematician had discovered it 25 years earlier. His only independent discovery, even though somebody had already discovered it, letter D, Guillaume de L'Hopital. That's all he discovered. And he gets a rule named after him that we mention in every calculus class in the world. And you know what the worst part is? 99.9% of calculus teachers give full credit to L'Hopital because they don't even know the story. And very few people know that he actually stole this and many other things. Let's go to a new series that we'd like to call, let's come up with a name. The name of this new thing is going to be Math Rivalries. The third biggest math rivalry was in 1637.
the controversy between number 4 Fermat and number 3 Descartes. In 1636, Fermat had published the first idea ever of taking an equation and turning it into a picture called a graph. But Descartes came along in 1637, stole the idea, and we call it the Cartesian plane to this very day. Math rivalry number 2. In 1699, there was a major controversy when number 3 Sir Isaac Newton accused number 19 Leibniz of stealing all of calculus from him. But Leibniz was living in Germany, Newton was living in England. Leibniz had no idea he was actually co-discovering calculus. The court awarded both credit for calculus. The number 1 math controversy happened in 1696, and it was the worst of them all. Back in 1691, a very wealthy Frenchman, 30 years old, named Guillaume de l'Hôpital, met up with a very famous mathematician Johann Bernoulli, who was only 24 at the time and had just earned his PhD. From a super rich family, L'Hôpital offered Johann Bernoulli $30,000 in today's money for Johann to teach him everything he knew about math. L'Hôpital was fascinated by mathematics, which is very much appreciated. But he took all of the unpublished ideas and discoveries that Johann Bernoulli shared with him, also took ideas from Jacob Bernoulli, his brother, and Gottfried Leibniz, a friend of the family, took all their unpublished discoveries of calculus, published it in a book, failed to give them credit, and took credit for the whole thing. The name of the book was Analyse des infiniment petits, which is the analysis of infinitesimally small things, the foundations of calculus.
Can you believe the nerve of L'Hôpital to take all that work and publish it as his own? Isn't that unbelievable? And can you believe that most calculus teachers don't even know, so they teach people L'Hôpital's rule? Oh yeah, it was discovered by Guillaume de l'Hôpital, if they even know that. No, it was discovered by the Bernoulli family and ripped off. Unbelievable. So here's one right here. I really want to call it Bernoulli's rule instead of L'Hôpital's rule, right? So we're going to take the limit as x approaches e of this really weird function. Okay, can you see that the e minus e is going to be 0 on the bottom? You can see that right there. Okay. All right. Can you see that the natural log of e is 1? We've done that before. Okay. Maybe we won't get indeterminate. Maybe we'll actually get an answer here. If you plug in e over here, the e's cancel. You get cosine of pi. The cosine of pi is a valley on the cosine graph, and all valleys are worth -1. That's 1 plus -1. That's 0 over 0. Big surprise. Okay, so we get 0 over 0. Okay, so that means we are allowed to use Bernoulli's rule, and we can do this. Limit as x approaches e of, take the derivative of the top. Natural log of x is 1 over x, right? Bernoulli was actually teaching this for $30,000 directly to L'Hôpital. L'Hôpital's taken all these notes, and I can appreciate that he was fascinated by mathematics, just like me. Then he publishes it, and then they name it after him. It's like, come on. All right, the derivative of cosine is negative. I'll leave a little gap. Sine of pi x over e, but then the chain rule. The chain rule of pi x over e, think about the x on the side, by the way. This trips up students sometimes. Think of it as pi over e x on the side. It's so much easier to see here. Isn't the derivative of number x just number? Always. Isn't the derivative of 3x 3? The derivative of pi over ex is just pi over e. That's your chain rule. Let's bump it up as a coefficient because it is a decimal, it is a number, it is a constant. It belongs as a coefficient. Matter of fact, it's the two most popular irrational numbers sandwiched together. Kind of cool. On the bottom, the derivative of x is 1, and the derivative of e is 0. Now we've escaped the indeterminate form. You take e, you plug it in for all the x's. So we get 1 over e minus pi over e, sine of e over e cancels, so it's just sine of pi. And you can just drop the over 1, of course, because it's just over 1. Sine of pi, okay, remember sine graph? It's an x-intercept. The sine of pi is 0. Gone. Final answer, 1 over e. There you go. Without L'Hopital or Bernoulli's rule, you couldn't do any of this stuff until this discovery. I want to go back in time and warn him, don't sell this stuff to L'Hopital. Just keep it to yourself and publish it later. All right, abracadabra. Okay, so take 1, try to plug it in. You know, it's worth it. 1 plus 1 is 2, and then minus 2, there's a 0 on the top. Cosine of pi is valley, -1, but then it's -1. So it turns it into a positive 1. Minus 1, it's 0 over 0. Of course it is. Okay, so L'Hopital's does apply. So let's do limit as x approaches 1 of 2x minus 2 plus 0 is the derivative. The derivative of negative cosine shall be positive sine of pi x. Chain rule of the base is pi. Put it in front. And then minus 1 is gone. Okay, there is our first derivative attempt. Take 1, plug it in the top. 2 minus 2 is 0. Okay. Well, as long as it's 0 over not 0, we're going to get the answer of 0. That's okay. If it's 0 over 0, though, we're still in the indeterminate world, right? Take a 1, plug it in. 1 times pi is pi. Sine of pi, x-intercept. 0 times pi. Still indeterminate. Let's try another L'Hopital's. Limit as x approaches 1 of derivative of the top is just 2. We've escaped. Derivative of the bottom, pi stays. Coefficients always stay. Derivative of sine is cosine of pi x times the chain rule, which is another pi, times the pi in front, which is pi squared. Okay? We rarely see pi squared in math, don't we, right? Very rarely. We see pi r squared, but hardly ever pi squared. Now plug in the 1. 1 times pi is pi. Cosine of pi is a valley, -1 times pi squared. It's 2 over negative pi squared. Although we never leave a negative on the bottom, so bump that up to the top. -2 over pi squared. By the way, there's a hole at 1 comma -2 over pi squared, whatever decimal that is. Page 3. So that brings us to the last problem, letter G. It's an infinite limit. Interesting. So x is going to approach infinity. All right, remember the 3 gems of infinite limits back in chapter 8, because those are going to come back again. They're going to be very handy. Gem number 1, just take infinity and plug it in there. Well, guess what you get? You get natural log of infinity. When you go to infinity, doesn't the natural log graph never stop rising even though it gets very shallow? The natural log of infinity is eventually infinity, even though it's so slowly rising. On the bottom, you get the natural log of infinity. That's also infinity. Well, that's indeterminate form number 2. You can't do things with infinity over infinity, but it is one of the L'Hopital forms. Okay. By the way, we also had like the weaker, stronger game, and then we had the third option, which was 1 over x to the highest power. Well, these aren't even polynomials, so like all that stuff's out. Total dead end. So kind of the fourth thing is, the last resort is, hey, maybe L'Hopital's rule works. Okay? So the limit as x approaches infinity. This is a great, great problem. I've seen this in college classes. The derivative of the top, the derivative of natural log, isn't that 1 over the base times the chain rule of the base, which is 1. The derivative of the bottom, isn't the natural log rule 1 over the base times the chain rule of the base, which is 2x. Okay, now here's what we're going to do. We're going to do 1 times 1 is 1. We're just going to combine those. We're going to do 1 times 2x because that's 2x over 1, right? So let's just make these into single fractions. Now wait a minute. If these are single fractions, 1 over x plus 1, and what's this one? 2x over x squared minus 1? If that's a fraction over a fraction, can't we just do a keep change flip? We can flip this one up to the side and make it into a multiplication problem. Okay, so this is not a L'Hopital step here. This is actually just like integrated 2, integrated 3, middle school. Okay, actually let's take out that fraction bar right there, because like I said, we're going to make it into a multiplication problem. Let's flip the other one right here. Okay, and still not calculus, algebra, middle school. That is the difference of 2 squares. X squared minus 1 can always be written as x plus 1, x minus 1, correct? And I have been telling you this since integrated 3 and some of you integrated 2. always, always take advantage of the cross cancel if it's there. You can only do cross cancellation with multiplication. X plus 1, still aren't doing calculus except for the first step so far. This is just basic old algebra. The only thing left on the top, other than the 1, is x minus 1. On the bottom, the sole survivor is 2x. Now, plug in infinity and do some calculus. You get infinity minus 1 is infinity, and 2 times infinity is an infinity. So, bad news. We're still stuck in indeterminate world. Good news. It's in one of the 2 L'Hopitalable forms. That's not a word, but that's okay. So, it means we can do L'Hopitals again. It's allowed. So, limit as x approaches infinity. Derivative of x minus 1 is 1. Derivative of 2x is 2. Well, I think we've escaped the indeterminate form now, because when you plug in infinity, there's no place to put the infinity because there are no x's. The answer is literally 1/2. All right? Go ahead, plug in infinity. There's nothing there. It's 1/2. So there's your final answer right there. Interesting. Okay? Now we go to the last bit of the story, because there's a little bit more to the story. And for that, we will end off today with another history break. De L'Hopital released his book of unpublished calculus gems. He was considered a genius comparable to Sir Isaac Newton, Fermat, and even Leibniz. Johann Bernoulli was considered paranoid, a fraud, accusing L'Hopital of plagiarism. There was a letter that had been written in 1694 from Bernoulli to L'Hopital, explaining what we now call L'Hopital's rule and many other things. And it was located tucked into an old book in a library in the city of Basel, Switzerland, the hometown of the Bernoulli family and Euler. But it wasn't discovered until the year 1921. 225 years later, and too late to apologize to the Bernoulli family. But L'Hopital was knocked out of the top 10 after his fraudulent behavior was exposed. Now let's go to the next thing that it says. By L'Hopital, oh, stupid. E, which we remembered, and Jacob was actually Johann's older brother. Let's try letter D. Oh boy, there we go. Hope this doesn't make it onto YouTube.